Welcome to Calm and Clever. It's lovely to have you here tonight. Wherever you are right now, settle in. Maybe you're lying in bed with the blanket pulled up, the room gone dark except for the soft glow of a screen. Maybe there's a lamp still on somewhere across the room, throwing a little warm light onto the ceiling. Maybe you're on a couch or a train or curled up somewhere far from home. Wherever you are, and whatever time it is in your corner of the world, I'm glad you found your way here. And before we drift into tonight's story, let me ask you the same thing I always ask. Where in the world are you watching from? Leave it in the comments if you feel like it, whenever it suits you. There's something quietly lovely about knowing that somewhere out there, a whole scattering of people are listening to the same soft voice at the same time, in the dark, all of them trying to fall asleep. You're not alone in that. You're part of a little nighttime crowd spread right across the planet. If you enjoy these slow journeys and you'd like more of them, a gentle like and a subscribe really do help this sleepy little channel keep going. Small creators like me lean on that more than you'd think. And to those of you who are already subscribed, who come back night after night, thank you. Honestly, you're the reason this room stays lit. Now, a small promise before we begin. I'm going to try not to make this so interesting that it keeps you awake. But if it does, well, at least you'll have learned something beautiful before morning. A fair trade, I think. And here's the most important part. You don't have to follow every word. You don't have to understand all of it. If you drift off halfway through, that's not a failure. That's the whole point. The ideas will still be here in the morning. The sun will still be shining. You can come back to it tomorrow night or the night after. There's no test at the end. There's no rush. There's only the slow, quiet pleasure of being told a true story while you fall asleep. So let your shoulders drop a little. Let your breathing slow down. And let me tell you something strange and lovely about the light that touches your face every single day. Here it is. The sunlight that warmed your skin this afternoon, the light that came slanting through a window, that lit up the dust in the air that you maybe didn't even notice. That light is older than human civilization. It is older than every city ever built, older than the pyramids, older than writing, older than the wheel. By the time it reached your face, it had already been on a journey so long that it makes the entire history of our species look like a single afternoon. That sounds like an exaggeration. It isn't. It's just true, and almost nobody ever stops to say it out loud. Because here's the thing we get told over and over. We're told that sunlight takes about 8 minutes to reach the Earth. And that's correct. The light crosses the vast, empty gap between the sun and us in roughly 8 minutes and 20 seconds, traveling at the fastest speed anything can travel. 8 minutes to cross all that space. But that 8 minutes is only the very last step, the final leap, the easy part. Before that light could cross space at all, it had to get out of the sun. And getting out of the sun, as we'll see tonight, is the slowest, strangest, most patient journey in the whole sky. It can take tens of thousands of years. In some honest estimates, well over 100,000 years, longer than humans have had cities, longer than we've had farms, longer by far than we've been writing any of it down. Tens of thousands of years to escape the sun, 8 minutes to cross the void, and then finally to fall onto your face on an ordinary afternoon, soft enough to make you sleepy. That's the story I want to tell you tonight. The quiet science of how starlight is made. We're going to follow a single tiny packet of light from the moment it's born in a place hotter and denser and stranger than anywhere you could ever stand, all the way out into the open and then across the dark until it reaches an eye like yours. We'll find out why it takes so impossibly long. We'll find out why the sun shines at all, which turns out to depend on a loophole in the laws of physics that almost shouldn't exist. And by the end, we'll look up at the night sky and read it like a thermometer, except the thermometer runs backwards, and once you see how, you'll never look at the stars quite the same way again. But that's later. We'll get there slowly, one mystery at a time. For now, let's go all the way down. Down past the surface, down through the layers, all the way to the very center of our sun, to the place where the light is born. Let's begin, shall we? To get to the heart of the sun, you'd have to travel inward through more than 400,000 miles of glowing matter. The sun is enormous. It's about 1,400,000 kilometers across, wide enough to swallow more than 1 million Earths, and almost all of that vast body is just an outer cloak, a blanket of hot gas, layer upon layer of it, wrapped around the one small region where everything actually happens. Because the fusion, the real engine of the sun, the place where new light gets made, happens only in the very core. And the core is small, surprisingly small when you think about how big the sun is. It fills only the innermost quarter or so of the sun's radius, just the central 25%. Everything outside that, the other 3/4 of the way out, is not making any new energy at all. It's just carrying it slowly outward. The core is a small, bright furnace buried inside a very large, very thick coat. And yet that small core, that innermost quarter, contains more than 99% of all the energy the sun ever generates. Think about that for a moment. The part that's actually doing the work is a tiny fraction of the whole, and it does almost all of it. The sun is mostly just the wrapping around, the gift. So what is it like down there in the core? It is hot, hotter than you can really picture. So let me give you the number and then we'll try to make it mean something. The temperature at the center of the sun is around 15 million Kelvin. Kelvin is just the scientist's way of measuring temperature, starting from the coldest possible cold, from absolute zero, so the number climbs the same way our degrees do, only without the negatives. 15 million of those. 15 million degrees. Now your body sits at about 37. A hot summer day might reach 40. An oven, a couple of hundred. A blacksmith's forge, glowing orange, maybe 1,500. The surface of the sun itself, which we'll get to, is a few thousand. And here, in the core, we are at 15 million. The numbers stop meaning anything ordinary at that point. There is nothing in your daily life that comes within a whisper of it. It is hot beyond any heat you have ever been near or ever will be. And it is at exactly that almost unimaginable temperature in only the innermost quarter of the sun that the light of every sunny day you've ever lived through was first kindled. But heat is only half of what makes the core strange. The other half is how crushingly, impossibly packed together everything is down there, because the core isn't just hot, it is dense, astonishingly dense. Let me put a number to it and then let's sit with it gently, because it leads to one of the loveliest little paradoxes in all of this. The density of the sun's core is around 150 grams in every cubic centimeter. A cubic centimeter is small, about the size of a sugar cube or the tip of your thumb. And in that little thumb-sized space, in the core, there are 150 grams of matter packed in. To feel what that means, picture lead. Lead is one of the heaviest, densest metals you can pick up. A small lead fishing weight feels absurdly heavy for its size, doesn't it? It seems to want to pull straight through your palm. The sun's core is about 13 times denser than lead. 13 times. So you might think, well, it must be solid then, solid like metal or harder, some crushed, fused, immovable lump at the center of the sun. And that would be a perfectly sensible guess, but it's wrong, and the way it's wrong is wonderful. The core of the sun is not solid, it's a gas. I know, 13 times denser than lead, and still a gas. How can that possibly be? Here's the answer, and it's a calm one. Things turn solid when they get cold enough, or rather when they're not too hot. The atoms slow down, settle into place, lock arms with their neighbors, and hold still. That's what solid means. Everything sitting in its proper spot. But in the sun's core, it's far, far too hot for anything to settle into anything. The heat is so violent that the atoms can't hold still for an instant. They can't lock together. They're torn apart even, the electrons stripped clean off their nuclei, everything moving at tremendous speeds, never pausing, never settling. So even though there's an enormous amount of matter crammed into a tiny space, denser than any metal you could ever hold, it can never condense into a solid because it's simply too hot to stop moving. It stays a gas. Though scientists give this state of stripped-down, superheated gas a special name. They call it a plasma. It's the same stuff that glows inside a neon sign or a lightning bolt, only here it is unimaginably more extreme. So picture it, the heart of the sun, denser than lead by far, hotter than anything in your world by a factor of millions, and yet still, somehow, a kind of gas. A gas you could never touch, never hold, never even approach. A paradox at the center of every sunrise. And what is squeezing all of that matter together so tightly? What's doing the crushing? Gravity. The sun's own gravity. Its weight pressing in on itself. Remember how huge the sun is, all of that matter, the entire outer blanket, all million times Earth's worth of it. Every layer is being pulled inward by gravity. And it all bears down, layer upon layer upon layer, until the full weight of the entire sun is pressing in on that small central core. The core is holding up the whole rest of the star. It carries the weight of everything above it. And so the pressure down there is staggering. The number is around 250 billion atmospheres. One atmosphere is just the ordinary weight of the air pressing on you right now, which you don't even feel because you've lived in it your whole life. The core of the sun feels 250 billion times that, a weight so enormous there's really nothing to compare it to. It is simply the entire gravitational might of the sun, all of it, focused inward onto its own heart. Now here's a question that you might think to ask, lying there in the dark. If gravity is forever crushing the core inward with all that unthinkable weight, then why doesn't the sun just collapse? Why doesn't the whole thing cave in on itself, fall inward, crumple down to nothing under its own enormous weight? That, it turns out, is one of the most beautiful questions in all of physics. And the answer is a kind of balance, a standoff, a truce between two titanic forces that has been holding quietly for billions of years. Here's how it works. Gravity pulls inward always, trying to collapse the star, trying to crush the core smaller and smaller. But the core is also doing something. Down there, the fusion is making energy, making heat, making light, pushing outward. The heat wants to expand. The radiation streaming out of the core pushes against everything above it. And the pressure of all that hot, fast-moving gas pushes outward too, trying to puff the star up, trying to make it bigger. So you have two opposite forces, gravity squeezing in, heat and radiation and pressure pushing out. And the remarkable thing, the thing that lets the sun exist at all, is that these two forces are almost perfectly, exquisitely balanced. Inward pull, outward push, matched so closely that the sun neither collapses nor explodes, it just holds. Steady, poised, balanced on a knife's edge that somehow never tips. Scientists have a name for this gentle, perfect standoff. They call it hydrostatic equilibrium. It's a long phrase, but the idea underneath it is simple, and it's calming, really, when you sit with it. Equilibrium just means balance, a balance between the crushing weight of gravity and the outward push of all that fusion-born heat. Two enormous forces, each one strong enough to destroy the sun on its own, holding hands instead, keeping each other in check. And here's the truly soothing part. This balance is self-correcting, it looks after itself. If the core fused a little too fast, made a little too much heat, the extra push would expand the core slightly, spreading it out, cooling it, which would slow the fusion back down. And if it ever fused a little too slowly, made too little heat, gravity would win for a moment and squeeze the core a touch tighter, which would heat it up again and speed the fusion back up. It nudges itself. It steadies itself. Push too hard and it eases off. Slack off and it tightens up, forever finding its way back to the middle. People sometimes call the sun a controlled bomb, and there's truth in that. It has all the raw power of an unimaginable explosion locked up inside it. But it never goes off all at once because it regulates itself moment by moment, holding that delicate balance between collapse and detonation. It is, if you like, the most patient explosion in the universe. A bomb that has agreed very gently never to explode. And how long has it been holding this balance? How long has the sun been quietly steadying itself, keeping that truce between gravity and heat? About 4.5 billion years, 4.6 billion to be a little more precise, since long before the Earth had oceans, long before there was anything alive to look up at it. The sun has been balanced on that knife's edge, never collapsing, never exploding, just shining steadily for 4.5 billion years. And it will go on doing so in this calm equilibrium for billions of years more. Sit with that for a moment as you're lying there, above you, beyond the ceiling, beyond the clouds, beyond the blue of the daytime and the black of the night. There is a balance that has held for 4.5 billion years and has never once broken. A steadiness older than the ground you're lying on. There's something restful in that, I think. The thing that gives us all our light and warmth is not frantic. It is not straining. It is, in its own way, perfectly calm, perfectly poised. It has found its balance and it simply holds it, night after night after night, the way you're trying to find yours now. But I've left something out. I've told you the sun is a controlled bomb that has refused for 4.5 billion years to go off. I've told you it balances itself, that gravity and heat are matched almost perfectly, but I haven't told you why the fusion happens so slowly and steadily in the first place. Why doesn't the sun just burn through all its fuel in a sudden flash? Why doesn't it fuse everything at once and tear itself apart in an instant, the way a real bomb does? Because here is something genuinely strange, and we'll unravel it slowly together when we go deeper. The reason the sun is so calm, the reason it burns gently and lasts for billions of years instead of detonating in a heartbeat, comes down to a single particle. A particle that almost never ever does the thing it would need to do to keep the fire going. The whole, steady, patient, life-giving light of the sun rests on something that should hardly ever happen at all. An event so rare it borders on the miraculous. And we'll see soon exactly why. But first, let's stay down here in the core a little longer, in the heat and the crushing weight, and look closely at what's actually happening to the matter itself. Because before any light can begin its long, slow climb to the surface, before it can ever fall on your skin, something has to make it. Something has to take the raw stuff of the sun and turn it, piece by piece, into light. And the way it does that is one of the quietest miracles in all of nature. So let's go closer still, closer than lead, closer than any place a person could ever stand, right down to the smallest pieces of the sun, and watch how, in the dark crush of the core, the very first spark of every sunbeam is struck. Down here, at the center of everything, the numbers stop sounding like numbers and start sounding like a place. 15 million Kelvin. Say it slowly and it's just a figure on a page, the kind of thing you'd nod at and forget. But sit with it for a moment, the way you'd sit with the warmth of a bath before you sink in. 15 million degrees. the hottest thing you have ever felt in your life, the searing edge of a stovetop, the breath of a bonfire on a cold night, all of that is barely a whisper next to this. There is no word in everyday language for heat like this, because nothing on earth, nothing you could ever stand near, comes even close. And this fire isn't spread evenly through the sun. That's something I find quietly lovely, and I want you to hold on to it. The part of the sun that actually makes the light, the engine room, where the energy is born, is much smaller than you'd think. It's only the innermost quarter of the sun, just the very heart of it. The deepest 25% of the way out from the center. And yet that small, hidden core does almost all of the work. More than 99% of the sun's energy is made right there, in that buried place none of us will ever see. Everything above it, all those hundreds of thousands of kilometers of glowing matter, all of that is really just the journey out. The making happens here, in the quiet middle. So picture the sun for a moment, not as a flat yellow disk in the sky, but as a vast sphere with a small, fierce ember at its very heart. The ember is the only part that burns. Everything else is the long, slow path that light has to take to leave. The sun is mostly a journey, only its tiniest, deepest part is a fire. Now here is where it gets strange in a way that's genuinely hard to picture, and I want to give it room, because it's one of those facts that quietly turns your idea of the world inside out. Down here, in the core, the matter is packed together so tightly that it is denser than any metal you have ever held. Denser than iron, denser than gold. About 150 grams in every cubic centimeter, which is roughly 13 times denser than lead. Think about that. Lead is so heavy that a small bar of it surprises your hand, sinks in your palm like it's pulling toward the ground. And the heart of the sun is more than 10 times heavier still, packed into the same little space. And so you'd expect it to be solid. You'd expect it to be the hardest, most stubborn substance imaginable, a dense metal heart at the center of the star. But it isn't solid at all. It's a gas. It's still somehow a gas, even at 13 times the density of lead. How can that be? How can something heavier than any metal still be a kind of gas? It comes back to the heat. It comes back to those 15 million degrees. The temperature down here is so impossibly high that the matter simply cannot settle. It cannot condense, cannot cool into a solid, cannot hold any fixed shape. The heat keeps every particle moving so violently, so endlessly, that even crushed 13 times tighter than lead, it stays a churning, restless gas. A plasma, to be precise, which is just a gas so hot that its atoms have been torn apart into the bare pieces underneath. But the picture I want to leave with you is gentler than the physics. The heart of the sun is a thing denser than any metal, and yet you could never hold it, never touch it, never set it down. A weight without a shape, a heaviness made of pure motion. And there's a reason it's packed so tightly. The reason is the simplest, oldest force there is, gravity. The whole enormous body of the sun, every layer of it, all that overlying weight, presses down toward the center. And the deeper you go, the more of the sun is sitting on top of you, bearing down. By the time you reach the core, the entire mass of the star is pressing inward, all of it leaning on this one small place. The pressure here is almost beyond imagining, something like 250 billion times the pressure of the air around you right now as you lie there breathing softly in the dark. 250 billion atmospheres. The air in your room, the air you don't even feel, the air that seems like nothing at all is already pressing on you all the time. And this is that 250 billion times over. Gravity, doing what gravity always does, just on a scale our bodies were never built to feel. It wants to pull the whole sun inward, to collapse it down to a point, to crush this enormous star into nothing. So why doesn't it? Why doesn't the sun simply fall in on itself under all that weight? Here is the answer, and it's a beautiful one, and it's been true for a very long time. Pushing outward against all that crushing gravity is the heat. The energy made in the core, the light being born there, pushes back. It presses outward just as hard as gravity presses in, and the two are matched, almost perfectly matched. The inward pull of gravity and the outward push of heat and light are balanced against each other, neither one winning, neither one losing, holding the sun in a kind of standoff that has lasted a very, very long time. Scientists have a name for this. They call it hydrostatic equilibrium, which is a heavy phrase for something almost peaceful. It just means the sun is in balance, the crush of gravity trying to collapse it, and the push of its own fire trying to blow it apart, perfectly cancel. And so the sun simply holds. It doesn't fall in, it doesn't fly apart. It just is the way it has been for about 4.5 billion years, 4.6 billion, give or take. Longer than there has been life on Earth in any shape you'd recognize, longer than the oceans, longer than the continents in their present arrangement. All that time, this one quiet balance, holding steady in the dark. And when you really sit with what that balance is, it becomes almost unsettling in a soft way. Because think about what's actually happening here. You have unimaginable heat, fusion, the same kind of process at the heart of the most violent weapons humans have ever built. And you have unimaginable gravity, enough to crush a star. Two enormous opposite forces, each one capable of destruction on a scale we can't picture. And instead of either of them winning, instead of an explosion or a collapse, you get this, a steady glow. A gentle, even light, that has been falling on this planet, on the leaves and the water and the faces of everything that ever lived for billions of years without a single break. In a way, the sun is a bomb, a genuine bomb with all the raw ingredients for catastrophe sitting right there in its core. But it's a bomb that holds itself perfectly still, a controlled explosion balanced so finely that it never goes off, never collapses, never even flickers in a way we could notice. It regulates itself quietly, without anyone tending it. If the core gets a little too hot, it pushes out and cools. If it cools a little too much, gravity squeezes it back and warms it again. Back and forth, a self-correcting fire, keeping its own balance through all those billions of years. Nobody set it, nobody watches over it. It simply found this steadiness on its own and has kept it ever since. There is something deeply restful in that, I think. The most powerful thing in our sky, the engine that everything alive depends on, is not raging or roaring. It is balanced. It is patient. It is, in its own enormous way, calm. And that calm is not an accident, and it is not fragile. It is built into the very physics of the thing, a balance so stable it has outlasted nearly everything. But here's the question that quietly sits underneath all of this, and it's the one we'll follow next. A bomb, even a balanced one, still has to burn. The fire in the core still has to keep going, year after year, for billions of years, without ever flaring up too fast or guttering out. And that's the part that should be impossible, because the fuel in the sun's core is exactly the kind of thing that by every rule we know should either refuse to burn at all or burn through in a sudden, blinding flash and be gone. It does neither. It burns slowly, so slowly that it lasts 10 billion years. And the reason it burns so slowly, the reason this controlled bomb stays controlled, comes down to something almost absurdly small and almost absurdly rare. A single particle deep in the crush of the core that almost never does the one thing the whole sun needs it to do. The entire patient light of the sun, all 4.5 billion years of it, rests on an event so unlikely it should barely happen at all. And that's where we're going next, down past the heat and the weight and the balance to the smallest spark of all, and the reason the sun has the patience to keep us warm. So, let's follow it there. The fuel in the sun's core is hydrogen, or more precisely, it is hydrogen stripped bare. Protons, the tiny positively charged hearts of hydrogen atoms with their electron shells long since torn away by the heat. Billions upon trillions of them crammed together in that dense, luminous crush, moving fast, colliding constantly, pressing against one another in the dark. And what the sun needs, what it has always needed, what every star needs, is for some of those protons to stick together, to fuse, to join so completely that they become something new, something heavier, something that carries more of the sun's fire forward. What the sun is doing at its very deepest point is alchemy. Old, slow, nuclear alchemy. And the recipe for it, written in the language of physics rather than myth, goes something like this. Take 4 hydrogen nuclei, 4 protons, bring them together in the right conditions through a chain of steps that is almost unimaginably improbable at each stage. And at the end of that chain, you will have one nucleus of helium-4, one neat, tightly bound package of 2 protons and 2 neutrons, plus 2 particles called positrons, which are like electrons, but with a positive charge, and 2 particles called neutrinos, which are almost nothing at all, barely there, ghosts of the process, and yet among the most important messengers in all of physics, and energy, a quiet, enormous, patient release of energy. This is the proton-proton chain, the PP chain as physicists call it, and it is the engine inside every star of the sun's size, the thing that has been running steadily in that innermost quarter of the sun's radius for 4.5 billion years without a pause. It is not complicated in outline. 4 protons in, 1 helium nucleus out, plus some byproducts, plus energy. You could write it on a card. But what the outline hides is the difficulty. The sheer, quiet, almost poignant difficulty of getting those protons to do what the sun needs them to do. Let's begin at the very first step, because the first step is the one that contains the whole secret. 2 protons are hurtling toward each other in the core. They are moving fast. Everything in the core moves fast, shaken by 15 million Kelvin of heat. And they collide. They press against each other. And for the fusion process to begin, one of those 2 protons has to do something extraordinary. It has to stop being a proton. It has to transform itself into a neutron, shedding its positive charge in a burst of particles called beta plus decay, driven by something called the weak nuclear force. And it has to do this at the exact moment of contact, not before, not after. At the instant the 2 protons are touching. The result, if everything goes right, is not 2 protons anymore. It is a deuterium nucleus. Hydrogen 2, a proton and a neutron bound together. And from there the chain continues. The deuterium picks up another proton and becomes a light helium nucleus. And then 2 of those light helium nuclei meet and produce 1 helium-4 plus 2 spare protons back into the mix. But it all hangs on that first step, that single transformation, that moment when 1 proton becomes a neutron exactly when it needs to. And here is the thing about that moment. How often do you think it happens? How often, in a place where protons are colliding with each other millions of times a second, does a given proton successfully complete that first step of fusion and make a deuterium nucleus? On average, and this is true, and the number is almost impossible to hold in your mind, on average, a single proton in the sun's core waits about 1 billion years before it successfully fuses. 1 billion years. A proton born in the sun today may still be waiting, still colliding, still failing to transform long after the Earth itself has been sterilized by the Sun's old age. Protons in the Sun's core are patient in a way that makes civilizations look like mayflies. The first step of fusion is not just rare, it is one of the rarest things that physics permits to happen, and this, if you will let it settle, is actually deeply comforting, because it means the Sun cannot rush. It is physically incapable of burning through its fuel quickly. The rate of fusion is not set by the temperature or the pressure. Those are high enough that the reactions could, in principle, be much faster. The rate is set by the weak nuclear force, by how rarely that proton-to-neutron transformation happens. The Sun is slow because it is waiting, all the time, at every point in its core, for an event that almost never occurs. And because that event almost never occurs, the Sun has been burning for 4.5 billion years and has roughly 5 billion more to go. The patience is structural, the patience is written into the physics, and it is the reason we are here at all. Imagine for a moment if the Sun burned faster, if fusion were easier, if protons merged on the first collision instead of the billionth. The Sun would have blazed through its hydrogen in millions of years rather than billions, too fast for planets to cool, too fast for oceans to form, far too fast for anything complicated to evolve. The rare, improbable difficulty of that first fusion step is indirectly the reason life had time to exist. The cosmic engine runs slowly because it is almost broken, always. And almost broken is exactly what we need. So the process is slow, but you might wonder, it is still happening, isn't it? Somewhere in the core, protons are still fusing. The energy is still being made. And if the Sun's core is 15 million Kelvin, and if the protons are still colliding constantly, then surely the ones that do fuse are being pushed together by the heat, by the speed of their motion. Surely they are moving fast enough to overcome their mutual repulsion and press together until the weak force has its chance. And here is where we reach something truly startling. Something that most explanations of the Sun quietly skip over, because it is a little harder to explain and a little more unsettling when you first hear it. The answer is no, the temperature is not enough. The protons in the Sun's core are not moving fast enough to push past each other by brute force. They never actually touch classically. They are always kept apart by something called the Coulomb barrier. Let me explain what that means. Two protons both carry a positive electric charge, and like charges repel each other. As two protons approach each other, the repulsion between them grows stronger and stronger, a wall of electrical force that pushes them apart. To fuse, they would need to get close enough that a different force, the strong nuclear force, which only acts at extremely short range, can grab them and hold them together. But to get that close, they would have to push through the Coulomb barrier. They would have to have enough energy to climb over the wall. At 15 million Kelvin, the protons in the Sun's core are moving fast, but they are not moving nearly fast enough. If you calculate the average speed of protons at 15 million Kelvin and compare it to the height of the Coulomb barrier, the numbers don't work. The protons are short of the energy they'd need by a significant margin. Classically, by the ordinary rules of motion that govern everyday objects, the rules Isaac Newton wrote down, the Sun's core is not hot enough for fusion. The protons cannot reach each other, and yet the Sun shines. If you are lying there in the dark, and that sentence gives you a small, strange feeling, that's exactly the right reaction. Because it means the Sun's light is not produced by anything in classical physics. The ordinary rules, the ones that describe a ball rolling down a hill or a billiard ball glancing off another, do not explain how the Sun shines. Something else is happening. Something that only makes sense in the language of quantum mechanics, that something is called quantum tunneling. In quantum mechanics, particles are not tiny billiard balls with well-defined positions and speeds. They are described by waves, probability waves, spread out over space. And one of the consequences of that wave nature is something that has no equivalent in everyday experience. A particle can be found on the other side of a barrier it did not have enough energy to climb over. Not by going through a gap in the barrier, not by being given extra energy, just by being there on the other side without ever classically crossing. The analogy I find most useful is a little strange, but stay with it. Imagine you roll a ball at a hill. You do not give it enough speed to reach the top. The ball rolls up, slows, stops, rolls back down. That is classical physics. That is everything you can observe at human scales. The ball stays on your side of the hill, but if the ball were a proton, or an electron, or any quantum particle, there would be a small but non-zero probability that it would appear on the other side of the hill anyway. It did not go over. It did not go around. It just tunneled through, as if the hill were not entirely solid to it, as if the barrier were more of a suggestion than an absolute rule. This is not a metaphor. This is not an approximation. This is what quantum particles actually do, measurably, repeatedly, and it has been confirmed in laboratory experiments countless times. And in the sun's core, this tunneling is not a curiosity. It is the entire mechanism. Protons approach each other, and when they get close enough that the barrier is thin enough, there is a small probability that one of them will tunnel through the Coulomb barrier and find itself on the other side, close enough for the strong nuclear force to take hold, close enough for the weak force to have its chance, close enough for fusion to begin. The probability is tiny. It is the reason a given proton waits 1 billion years. Each collision has only an infinitesimal chance of producing tunneling, and an even smaller chance of combining the tunneling with the weak force transformation needed for deuterium formation. But the core contains an almost incomprehensible number of protons, all colliding constantly, and over time, long, patient time, it happens, again and again. Not often by any measure we can intuitively grasp, but often enough to power a star. Without quantum tunneling, the sun would not shine. Not dimmer, not differently, not at all. The Coulomb barrier would be absolute. The protons would bounce apart forever, and there would be no fusion, no light, no warmth. Every star in the sky depends on this quantum loophole. Every photon of light that has ever reached your eye from the night sky was born because of a rule that classical physics doesn't even allow. That, if you will forgive me saying so, is extraordinary. You are lying in the warmth of a star that is powered by a mechanism that shouldn't work by the rules of the physics we can see with our eyes. And it has been quietly working this way for longer than the continents have had their current shapes. Let's follow what happens after the tunneling succeeds, after the proton-proton chain runs its course, and the helium-4 nucleus is sitting there, newly made, in the core. Because there is something about that helium nucleus that carries the energy of the whole process, and it is worth understanding what it is. A helium-4 nucleus is made of 2 protons and 2 neutrons. And if you were to very carefully weigh those 4 particles separately, and then weigh the helium nucleus they form together, you would find a discrepancy. The helium nucleus is lighter, not by much, about 0.7% of the total mass, but lighter. Some mass has gone missing. It has not, of course, truly gone missing. It has become energy. This is E equals mc squared, Einstein's most famous equation, in its most literal and consequential application. The missing mass, to be that 0.7%, has been converted directly into energy, into photons, into heat, into the light that will, in 100,000 years or so, reach the surface and begin its 8-minute journey to your eye. The number attached to this is worth sitting with for a moment because it is both staggering and, in context, almost gentle. Every second, the sun fuses roughly 600 million tons of hydrogen into helium. 600 million tons, a number so large it starts to lose meaning. But of those 600 million tons, only about 4 million tons become pure energy. Pure light, via E, equals mc squared. The other 596 million tons end up as helium, as changed but still present matter. 4 million tons of mass converted to energy every second. And yet the sun will keep doing this for another 5 billion years because it started with so much hydrogen that even this rate of consumption is a slow, patient sip from an ocean. The sun is not running out of fuel in any way that matters to the sleeping minds of anyone alive tonight. 4 million tons of mass per second sounds violent, and in one sense it is. The energy released is almost incomprehensible. 3.8 times 10 to the 26th watts of power pouring out in all directions, an output you cannot really visualize. But I want to offer you another way to think about it that is, I find, oddly calming rather than alarming. Think about where that energy is actually coming from, not from the sun as a whole, from the core, from that innermost 25% of the radius, that compact, dense, luminous heart. And here is the thing, the power density of the sun's core, the amount of energy produced per unit volume, is surprisingly, almost embarrassingly, modest. About 276 watts per cubic meter. That is the average rate at which the sun's core generates energy per cubic meter in the region of highest temperature and pressure in our entire solar system. And 276 watts per cubic meter is not an impressive number by earthly standards. A compost heap, a pile of damp leaves and vegetable scraps rotting in someone's garden, produces roughly comparable energy per cubic meter from ordinary biochemical decay. A reptile sitting in the sun warming itself produces energy at a somewhat similar volumetric rate. The sun's core, at 15 million Kelvin and 250 billion atmospheres of pressure, the place where quantum tunneling conjures energy from mass, generates power at about the rate of a moderately active compost heap. This seems like it cannot be right, and yet it is. The reason the sun is bright, blindingly, incomprehensibly bright, is not that its core is intense, it is that the sun is vast. The core alone is enormous by any terrestrial standard, and it contains so many cubic meters of gently humming, compost-level power output that the total adds up to those 3.8 times 10 to the 26th watts. The sun does not shine because it is a raging inferno at every point. It shines because it is simply so big. Spread across enough space, a moderate power density becomes a star. There is something in that, I think, that is worth carrying with you into sleep. We tend to picture the sun as violent, extreme, the very image of raw power, and it is in aggregate. But at its smallest, most fundamental level, the level where the physics actually happens, it is almost serene. Two protons drifting together, waiting a billion years for their chance, making the leap through a quantum loophole, releasing a quiet fraction of their mass as light, and, per cubic meter, doing it at roughly the pace of a garden compost heap. The universe's most powerful engines run at the smallest scale on patience and probability. It is also worth noting, while we are here, what kind of burning the sun is actually doing. Because we say the sun burns, we say stars burn, and the word carries the image of fire, of a flame, of oxygen, and fuel combining in a chemical reaction. But there is no fire in the sun, there is no flame, there is no oxygen being consumed. The sun is not burning in any chemical sense. The word is a metaphor, and like many metaphors, it obscures as much as it reveals. What the sun is doing is nuclear fusion. It is rearranging atomic nuclei, not molecules. No oxygen is needed or involved, no combustion reaction is happening. The energy comes not from electrons shuffling between atoms, the way candle flames and bonfires work, but from the nucleus itself, from the mass-to-energy conversion that happens when protons and neutrons rearrange into a more tightly bound configuration. The energy scale is millions of times larger than chemical reactions, which is why a fusion-powered star can keep going for billions of years, where a chemically burning sun would be cinders in a few thousand. So there is no flame. There is no roaring fire. There is only the deep, quiet, improbable nuclear alchemy of the proton-proton chain, running slowly, step by step, one tunneling proton at a time in the dark at the center of the world. And there is one more character in this story that I have not properly introduced yet, one that plays a quiet but crucial role, not just in the physics, but in our understanding of it. When the proton-proton chain runs, it produces two kinds of product. We have spoken of the helium nucleus and the energy, but it also produces something else, those two neutrinos I mentioned briefly, one at an early step in the chain, one at another. Neutrinos are, if you will forgive a slight digression into the almost nothing, remarkable. They have almost no mass, a tiny fraction of even an electron's mass, which is itself tiny. They carry no electric charge, they interact with almost nothing, they pass through ordinary matter as if it weren't there, because to them, for all practical purposes, it isn't. A neutrino created in the sun's core does not wander and zigzag and spend 100,000 years making its way out. It simply leaves. In about 2 seconds, it has traveled from the core to the surface and is gone, already racing through space. It reaches Earth about 8 minutes later. The same journey that takes a photon of visible light 8 minutes once it finally escapes the surface. And here is something that is, if you think about it, one of the quieter marvels of an ordinary night. About 65 billion solar neutrinos pass through every square centimeter of your body every second. Right now. Whether the sun is up or down. If you are lying in the dark, the sun is below the horizon, but the neutrinos don't notice. They pass through the entire bulk of the Earth as though it is not there at all. The rock, the iron core, the mantle, all of it, and arrive at you from below, coming up through your mattress, through the floor, through miles of solid ground, without a flicker of interruption. The Earth is transparent to them. So are you. 65 billion per square centimeter every second, day and night throughout your life. And you feel nothing. You detect nothing, because nothing in your body is equipped to detect them. They simply pass through, leaving no trace, taking their information from the core of the sun with them and carrying it out into the universe, never to interact with ordinary matter again. This is the thought I find most quietly astonishing about the sun. Not the heat, not the pressure, not even the quantum tunneling, but this. Right now, while you are lying still and the night is quiet, the sun is sending you messages, direct messages from its core, from the place where the fusion actually happens, unimpeded, unaltered, traveling at nearly the speed of light. And they are passing through you, and you cannot feel them, and they will never stop. The neutrinos are the only direct messengers the core has. Every other form of energy, every photon, every wave of heat has to fight its way out through the dense, opaque plasma of the sun's interior, bouncing and scattering for tens of thousands of years. But the neutrinos just leave, and so they carry the freshest possible news of what is happening in the core. News only seconds old when they reach the surface, 8 minutes old when they reach us. It is through neutrinos that we have our most direct confirmation that the proton-proton chain is really happening, that the model is right, that the sun really is doing what we think it is doing, and that confirmation did not come easily or quickly. It took decades of careful, frustrating work, and the answer revealed something new and unexpected about the neutrinos themselves. But that is a thread we can follow a little later when we talk about how we know any of this is true. how we look at the sun, which we can never visit or touch, and read from it a story as detailed and trustworthy as a laboratory experiment. For now, let the picture settle. In the core, every second, 600 million tons of hydrogen becomes slightly less than 600 million tons of helium, and the missing 4 million tons become energy. The mechanism is the proton-proton chain, driven not by brute heat, but by a quantum loophole that lets particles pass through barriers they cannot classically cross. The process is slow almost beyond imagining, 1 billion years per proton on average before the first step succeeds. And that slowness is the sun's patience, the reason it is still here, the reason it will still be here long after everything you have known is gone. The energy is born here, in the dark, as photons. Gamma rays, high energy and lethal, the kind of radiation that in any ordinary context would mean catastrophe. They are born in the hottest, densest, most extreme environment in the solar system, surrounded by a wall of plasma so thick that it will take those photons an almost geological span of time to escape. And here is the thing about that journey. We have been in the core watching the most patient process in physics. We have followed the proton that waited 1 billion years. We have watched the helium nucleus form and shed its tiny fraction of mass as light. We have felt the neutrinos pass through us without a goodbye. Now the energy has to go somewhere. The light that was born in the core has to reach you. And that journey, that slow, wandering, improbable journey through the body of the sun, is where the story takes its most unexpected turn, and where the number that most surprises people, the number almost no other telling of this story bothers to make vivid, finally arrives. The photon sets out, not toward the surface, not in any particular direction at all. It does not know where the surface is. It is absorbed by a nearby nucleus almost immediately, re-emitted in a random direction, absorbed again, re-emitted again. It staggers, it wanders, it takes one step and then another step, and they may be in exactly opposite directions. This is the journey that will take it not 8 minutes, not 8 days, not 8 years, but something closer to 100,000 years, give or take a wide margin that reflects just how difficult the calculation is. We will follow it there in a moment. Let's not rush. The photon has waited this long. But first, let us stay here a little longer, because there is something happening in the core right now, something we passed over quietly, that deserves to be understood before we follow the light on its long wandering. We said that 4 protons become 1 helium-4 nucleus. That is the net result, the summary. But what actually happens step by step is one of the strangest recipes in all of physics. The first step is the hard one. 2 protons approach each other. They are both positively charged, which means they repel. Think of trying to push the north poles of 2 strong magnets together. That resistance you feel in your hands, that invisible wall of force. Now imagine it is 10,000 times stronger, and the magnets are smaller than anything you could possibly see. That repulsion has a name: the Coulomb barrier. And it exists for a very good reason. Protons do not want to touch. They never want to touch. The entire history of the universe is mostly just protons not touching each other. To fuse, to actually become deuterium, a nucleus of 1 proton and 1 neutron bound together, one of those 2 protons must convert into a neutron. That conversion is handled by the weak nuclear force through a process called beta plus decay. And here is what makes the first step so extraordinarily improbable: that conversion has to happen at the exact instant the 2 protons are in contact. Not a moment before, not a moment after. At the precise, vanishingly brief instant that they are close enough, the weak force must reach in and flip a proton into a neutron, or the whole thing fails and the 2 protons bounce apart, unchanged, as if nothing happened. How long does a given proton typically wait before this works? About 1 billion years. A single proton drifting through the core of the Sun, surrounded by hundreds of billions of potential partners, bathed in heat and pressure beyond anything on Earth, waits on average 1 billion years before it successfully completes the first step. And this is not a flaw, this is the design. This profound rarity, this near impossibility of the first step, is precisely why the Sun is still here. If fusion were easy, if protons fused readily and quickly, the Sun would have burned through its fuel in a geological eye blink and gone dark long before the Earth had cooled enough for anything to live on it. The billion-year wait per proton is what gives the Sun its extraordinary patience. It is the throttle on the engine. The Sun has been fusing hydrogen for about 4.5 billion years, and it has enough left for roughly 5 billion more because the first step is so reluctant. Slowness here is a gift. But there is a deeper strangeness waiting beneath even this. We said the protons repel, we said the Coulomb barrier stands between them, and if you calculate using the ordinary laws of physics the temperature you would need to force two protons together to give them enough speed to simply ram through that barrier by brute force, the answer is far higher than 15 million Kelvin, far higher than the actual temperature of the Sun's core. In other words, the Sun's core is not actually hot enough for fusion to happen, not by classical physics, and yet it happens. The neutrinos escape. The helium accumulates. The light is born. You are here reading this into your pillow because somehow the Sun shines despite being, technically, too cold. The resolution is quantum tunneling. In the quantum world, a particle does not have a perfectly fixed position the way a marble does. It has a wave function, a kind of smeared probability of being in a range of places. And because of this smearing, there is a small but real chance that a proton will simply be found on the other side of the Coulomb barrier, even without having enough energy to climb over it. It tunnels through, not around, not over. Through the wall itself, the way a ghost is sometimes said to pass through a door. Except that this is real, and it happens billions of times every second inside the Sun. Without quantum tunneling, the Sun would not shine. Sit with that for a moment. One of the most classical, ancient, enormous things in our sky, that warm presence that has been rising over human campfires and fields and rooftops since before our species had language, is powered by a quantum loophole. It runs on a rule from the deepest and strangest layer of physics, the layer where particles are also waves and certainty dissolves into probability. The Sun is not a simple furnace, it is an enormously patient quantum machine. And then the mass. Once the chain completes, once 4 protons have finally, patiently, impossibly become one helium-4 nucleus, something is missing. You would expect the helium nucleus to weigh exactly as much as the 4 protons that went into it. It does not. It is lighter, about 0.7% lighter. A small fraction, almost nothing. But that missing mass does not disappear. It becomes energy through the most famous equation in physics, E equals mc squared. Mass times the speed of light squared. And because the speed of light is so enormous, nearly 300 million meters per second, even a tiny amount of missing mass releases a breathtaking flood of energy. The Sun converts about 4 million tons of its own mass into pure energy every single second. Every second. 4 million tons, keep the mass of roughly 2,000 large passenger aircraft, simply ceasing to exist as matter and becoming light instead. And to fuel that conversion, about 600 million tons of hydrogen are fused into helium every second. These are numbers so large they become a little dreamy. But there is something important underneath them. Something the numbers alone do not quite capture. The Sun is not doing this intensely. This is perhaps the most quietly astonishing fact in the whole story of the Sun, and almost nobody tells it. If you could take a cubic meter of the Sun's core, a box about the size of a washing machine, filled with plasma at 15 million Kelvin, and measure how much energy it produces, the answer would be about 276 watts. Not thousands of watts, not millions, 276. Roughly the output of 3 or 4 bright light bulbs, comparable to a healthy compost heap or the metabolic heat of a large reptile. The core of the Sun, gram for gram, cubic meter for cubic meter, is barely warmer in its energy output than a pile of garden waste. The reason the Sun shines so brilliantly, the reason it is visible in broad daylight from 150 million kilometers away, the reason it can warm your face through a window even in the middle of winter, is not because it is intense, it is because it is vast. The Sun contains an almost incomprehensible volume of core plasma, all of it quietly, patiently, producing its few hundred watts per cubic meter, and the sum of those unhurried contributions across that enormous volume adds up to nearly 400 trillion watts of total power. It shines not because it burns hot, but because there is so much of it. And this is the right word to use if we are being careful, not burn. Stars do not burn. There is no fire in the Sun, no flame, no oxygen, no chemical combustion of the kind you see in a candle or a hearth. Burning is a word we borrowed from our campfires and carried up into the sky by habit, by analogy, because the Sun looked to our ancestors the way fire looked. But what happens in the core is something older and stranger than fire. A nuclear process, a quantum process, a slow and patient transformation of hydrogen into helium and light at the level of individual atomic nuclei, one improbable collision at a time. Stars don't burn, they wait. And then very occasionally something tunnels through a wall that should not be crossable, and a little more helium forms and a little more mass becomes light, and the light begins its long, wandering journey outward. And that is where we meet the light itself. Not yet the light you see, not the gentle, familiar thing that filters through curtains on a Sunday morning or glimmers across the water at dusk. What we are talking about now is something born in the deepest, most extreme place in the solar system, a place of crushing density, of temperatures measured in the tens of millions of degrees, a place so far from anything we would recognize as ordinary that the word place itself feels like a stretch. A packet of energy is born in the Sun's core. It is born from that moment we have been tracing so carefully, from that extraordinarily improbable meeting of 2 protons, that billion-year waiting game, that quantum miracle of tunneling through a barrier that should have been uncrossable. The energy that results from fusion, from that 0.7% of mass that never becomes helium, that surrenders instead to Einstein's equation and transforms, that energy has to go somewhere. It becomes a photon, a particle of light, but not just any light. The temperatures in the core are around 15 million Kelvin, and at 15 million Kelvin, the kind of light that gets produced is not the soft amber glow of a reading lamp. It is not the pale blue of a clear winter sky. It is a gamma ray, the most energetic, most penetrating, most violent form of electromagnetic radiation that exists. A single gamma ray born in the solar core carries more energy than millions of ordinary photons of visible light. If you could hold one in your hand, which you cannot and never should, because it would pass through your hand and through you and keep going, it would represent a quantity of energy that, concentrated at that scale, is genuinely lethal. This is what Starlight is at the very beginning. Not a soft thing, not a gentle thing, a weapon by any ordinary reckoning, born in the most extreme furnace in our corner of the galaxy. and now it begins its journey out. Or rather, and this is the part that most tellings of the sun's story leave out, gloss over, skip past with barely a mention, now it begins something that can only very loosely be called a journey. Because a journey implies movement in a direction. A journey implies progress. And what happens to this gamma ray in the first few 100,000 kilometers of its existence is almost the opposite of progress. It is absorbed. Almost immediately, almost the instant it is born, it is absorbed by a nearby particle of plasma, a proton, an electron, an ion of some kind. And it ceases to exist as that photon. Its energy is taken in. And then, a tiny fraction of a second later, a new photon is emitted, not necessarily in any particular direction, in fact in a random direction, completely, utterly, indifferently random. And then that new photon travels a very short distance, a distance measured in centimeters perhaps, or millimeters, depending on the density of the local plasma, before it too is absorbed and re-emitted in another random direction, and again, and again. This is the drunkard's walk. This is what physicists call a random walk, and it is one of the most poetic and quietly devastating concepts in all of astrophysics, if you give yourself a moment to sit with it. Imagine, if you're not already drifting, if your eyes are still half open and your thoughts are still loose and wandering, imagine a person who has had a little too much to drink, standing in the middle of a very large, very crowded room. They want to reach the door, but they have no sense of direction. Every step they take is random. Forward, backward, left, right, at some angle, equally likely in any direction. Sometimes, by chance, they drift a few steps toward the door. But then chance pulls them back, or sideways, or in a direction that seems to make no progress at all. That is the photon. For every step that happens to aim outward, toward the surface, toward freedom, there are just as many steps pointing back toward the core, or sideways, or in directions that accomplish nothing in terms of net escape. The plasma of the sun's interior is so extraordinarily dense. Remember, we said the core is about 150 grams per cubic centimeter, 13 times denser than lead, that even in the somewhat cooler and less dense radiative zone that surrounds the core, a photon cannot travel more than a tiny fraction of a centimeter, on average, before it encounters another particle and is absorbed and re-emitted. The radiative zone extends from the edge of the core, from roughly the inner quarter of the sun's radius, all the way out to about 70% of the full radius. That is an enormous region of dense, hot plasma through which the energy must pass. And it must pass through it in this stuttering, staggering, completely directionless fashion, one random step at a time. Now, how long does this take? This is the number. This is the one that, when you really let it land, changes something quietly in how you look at a sunny day. It takes roughly tens of thousands of years. The range in published scientific estimates is actually quite wide, depending on how you model the sun's interior and what exactly you mean by the energy traveling. But the honest, well-supported answer is somewhere in the range of tens of thousands to 100,000 years or more. Some detailed models put it closer to 100,000 to 200,000 years. The honest thing to say is it is long. Extraordinarily, almost incomprehensibly long. Let us sit with that for a moment, because the number alone does not do it. Tens of thousands of years. Modern human beings, people who looked essentially like you and me, who had language and culture and the ability to wonder about the stars, have existed on this planet for roughly 100,000 years or so, by most estimates. The first cave paintings, the first signs of symbolic thought, the first buried dead, all of this sits within roughly the same time frame. Agriculture appeared only about 12,000 years ago. The oldest cities are perhaps 8,000 years old. Everything you think of as human history, Egypt, Rome, Greece, China, the Renaissance, the Age of Exploration, the Industrial Revolution, the entire recorded story of civilization, fits inside the last 5,000 or 6,000 years. And the energy that left the sun's core as a gamma ray that began its slow and drunkenly staggering random walk through the radiative zone might have begun that walk before any of that existed. Before your ancestors' ancestors planted the first seed, before the first city was built, before anyone scratched a story onto a clay tablet, before the pyramids were a thought in anyone's mind, the light you will see tomorrow morning streaming through your window, warming the room where you are lying right now. That energy may have been born in the sun's core and begun its wandering journey outward before the Bronze Age, before the Stone Age, perhaps before humanity had language at all. It took that long just to escape the star. And then, once it finally emerged from the surface, from that layer we will talk about in a moment, it took 8 minutes and 20 seconds to cross the 150 million kilometers of space between the sun and your eye. 8 minutes and 20 seconds compared to the 100,000 years or more inside. There is something almost unbearably poetic about that ratio if you are in the right mood for it. And perhaps at this hour, wherever you are exactly in the right mood. All that patience, all that staggering, wandering, directionless effort. And then, at last, open space. And in that open space, the photon moves at the only speed it knows, 300,000 kilometers per second, the speed of light, unconstrained at last, and the distance between a star and a planet is crossed in the time it takes to cook a soft-boiled egg. But we are getting a little ahead of ourselves. Let us stay just a little longer inside the sun, because there is another dimension to the random walk that is worth taking in slowly. It is not just the time scale that is astonishing, it is the distance. The sun's radius from its center to its surface is approximately 700,000 kilometers. That is the straight line distance from the core to freedom. In ordinary terms, that is enormous. The Earth's entire diameter is only about 12,000 kilometers, so you could line up roughly 60 Earths between the sun's core and its surface. But in astronomical terms, 700,000 kilometers is not so very large. Light in open space could cover it in about 2 seconds and 20 minutes. The photon doing the random walk does not cover it in 2 seconds and 20 minutes. Because it is not traveling in a straight line, it is zigzagging, it is absorbed, re-emitted in a random direction, travels a tiny distance, absorbed again, re-emitted in another random direction. And while its net progress toward the surface is achingly slow, taking, as we have said, tens of thousands of years or more, the total distance it travels, the sum of all those tiny random steps in all those random directions, is vastly, almost impossibly larger than 700,000 kilometers. When physicists have calculated the total path length of a photon's random walk through the sun, the sum of every tiny zig and every tiny zag, the cumulative distance of all those absorbed and re-emitted steps, the answer comes out in the neighborhood of several light years inside a single star. A light year is the distance light travels in 1 year through empty space, about 9.5 trillion kilometers. The Milky Way galaxy is roughly 100,000 light years across. The nearest star to our Sun, Proxima Centauri, is about 4 light years away, and a single photon doing its random walk through the interior of our Sun travels a path that could be measured not in kilometers, not in millions of kilometers, but in light years of cumulative distance, all within a ball of plasma that is only about 1.5 million kilometers wide. It travels a galaxy's worth of distance to escape a single star. That is the random walk That is the radiative zone. That is why it takes so long. There is a kind of patience in this that I find deeply calming, though perhaps patience is the wrong word for a process that has no intention, no awareness, no desire to escape. The photon does not want to reach the surface. It does not know it is imprisoned. It simply follows the laws of physics, step by random step, and the surface arrives eventually, not because the photon finds its way, but because, given enough time, even a drunkard stumbles through the door. And as it wanders, something else is happening, something remarkable, something that we will pay off completely before this night is over. The photon is changing. When it was born, when that first gamma ray emerged from the fusion reaction in the innermost core, it was an extraordinarily energetic thing. Gamma rays have very short wavelengths and very high frequencies. They carry enormous packets of energy per photon by the standards of the electromagnetic spectrum. They are not visible to the human eye. They sit far, far beyond the violet end of the rainbow, in territory that is invisible and dangerous. But as the energy stumbles outward through the radiative zone, it does not stay as a single gamma ray. When a photon is absorbed by a particle of plasma, and that particle later releases the energy again, it does not have to release it as a single new photon with the same energy as the one it absorbed. It can release several lower energy photons. The energy gets distributed, shared out, and as you move outward from the core toward the surface, the plasma gets progressively cooler. Still extraordinarily hot by any standard we know, but cooler than the 15 million Kelvin inferno of the center. Cooler plasma re-emits radiation that peaks at lower energies. The original gamma ray, that single, violent, high-energy burst, gradually gives way to a cascade of softer, lower-energy radiation. By the time the energy has made its way through the entire radiative zone, after its 100,000-year random walk, the radiation has shifted. It is no longer gamma rays. It is a mixture of forms, but a great deal of it has moved into the range of X-rays, and some of it into ultraviolet, and some of it nudging toward the lower end of high energy. The original packet of violence has been democratized, spread out, softened. It is not yet visible light, but it is on its way. And then it reaches a boundary, a transition. At about 70% of the sun's radius from the center, something changes in the nature of the solar interior. The physics of energy transport shifts. Below this boundary, when the radiative zone, energy moves staggeringly slowly as radiation, as photons doing their random walk. But above this boundary, in what we call the convective zone, a different mechanism takes over. The plasma in this outer region is cooler and less dense than the plasma deeper in, and it behaves differently. Instead of being transparent enough, even if barely, tortuously so, to carry energy by radiation, it becomes almost opaque. Radiation cannot make progress here the way it does, even slowly, in the radiative zone. And so nature finds another way. The plasma boils, not in the way water boils in a kettle, not with bubbles in any familiar sense, but with the same basic physics. A region of plasma deep in the convective zone absorbs energy from below. It gets hot. Hot things expand. Expanded plasma is less dense than the surrounding plasma. Less dense things in a gravitational field rise. So this hot blob of plasma rises. It carries its heat with it. Physically, bodily, the way a blob of hot wax carries its heat as it rises in a lava lamp. It rises through the convective zone toward the surface, and as it rises it expands further and cools. When it reaches the surface, it has given up most of its heat, radiated it away as light, dispersed it into the layer above, and now, cooler and denser than its surroundings, it sinks back down to absorb more energy and rise again. This is convection. It is the same process that circulates air in a heated room, that stirs the water in a pot on the stove, that drives weather patterns in the Earth's atmosphere. It is ordinary physics, familiar physics, the physics of warming and cooling and rising and sinking. And in the sun's outer third, it is what carries the energy the rest of the way to the surface. The convective zone is, in one sense, faster than the radiative zone. The plasma does not have to zigzag randomly, it flows in broad, sweeping cells of hot upwelling and cool downflow, but it is still not fast by any human measure. The large-scale convection currents in the sun's interior take on the order of a month or so to complete a cycle. And at the surface of the sun, at the photosphere, the layer we will come to in a moment, you can see the tops of the convection cells. They are visible in solar telescopes as a texture of granules covering the entire surface of the sun. Each granule is a convection cell seen from above, a hot blob of plasma that has risen to the surface, spread out, shed its heat as light, and is beginning to cool and fall back down at its edges. Each of these granules is roughly 1,000 kilometers across. For scale, the entire United States from the Atlantic to the Pacific is about 4,000 kilometers wide. A single solar granule is roughly the size of Texas, and there are about 2 million of them covering the sun at any given moment, forming a constantly shifting mosaic. Bright centers of rising hot plasma, darker edges of cooling, sinking material. Each granule lasts only about 8 to 20 minutes before it dissolves and a new one forms. The sun's surface, if we can call it that, is a ceaselessly simmering, constantly renewing mosaic of Texas-sized bubbles, each one living for less than half an hour, each one the top of a convection column that extends deep into the solar interior, each one quietly, efficiently carrying a fraction of the sun's enormous energy output toward the space where it can finally escape. There is something I find very quietly beautiful about that at this hour. 2 million Texas-sized bubbles simmering and dissolving and reforming in a surface mosaic that has been doing this without pause for 4.5 billion years. No two moments of the sun's surface have ever been exactly alike. And above the granulation layer, above the boiling top of the convective zone, we reach the layer that determines everything we know about the sun from the outside. The photosphere. The photosphere is the sun's surface, in the sense that it is the layer from which light finally escapes freely into space. Below the photosphere, the plasma is opaque, too dense, too full of free electrons and ions for light to travel any significant distance without being absorbed. The photosphere is where that opacity finally gives way to something closer to transparency. Its temperature is approximately 5,778 Kelvin, let us call it 5,800 Kelvin for simplicity, or about 5,500 degrees Celsius. After the 15 million Kelvin furnace of the core, this sounds almost modest. And in a sense it is. The surface of the sun is only 5,800 Kelvin because the sun's energy, after that 100,000-year stagger through the interior, has spread and diluted and cooled, the way a warm loaf of bread fresh from the oven eventually cools to room temperature if you leave it out. From the photosphere, the light that was born as a gamma ray and spent an epoch wandering the sun's interior is finally free. It has not completed its transformation yet. That will happen at the very end, and it is part of the payoff we are building toward, so let us hold it a little longer. But it is free. It steps off the photosphere and into the vacuum of space, and there, at last, nothing stops it. Nothing absorbs it and re-emits it in a random direction. It moves in a straight line at the speed of light, across the vast emptiness between the sun and whatever it happens to be aimed at. And perhaps after 8 minutes and 20 seconds of that unimpeded travel, it reaches the atmosphere of a small blue planet, and perhaps it reaches the surface of that planet, and perhaps it finds a window and falls through and lands on the face of someone lying in bed, half asleep. But before we step fully outside the sun, there is one more thread to tie. Because you might reasonably be wondering, and it is a very good thing to wonder, especially at this hour when the mind is loose and willing to follow a question wherever it goes, how do we actually know any of this? How do we know about the 15 million Kelvin core, the random walk, the 100,000-year journey? We have never sent a probe into the sun. We have never drilled down through its layers. The photosphere is the deepest we can see with light, and everything below it is hidden behind that opaque wall of plasma. We know it the way much of science knows its deepest truths, indirectly by proxy, by reading the signals that leak through when the thing itself cannot be observed. And the sun's core has a leak, a very specific, very revealing, extraordinarily useful leak. The proton-proton chain, the fusion reaction we traced so carefully, produces not just energy and helium. At each step, it produces neutrinos, 2 of them per completed chain, released alongside the energy and the positrons. And neutrinos, as we mentioned earlier in our walk through the core, are almost impossibly indifferent to ordinary matter. A neutrino produced in the sun's core does not do a random walk. It does not get absorbed by the dense plasma and re-emitted in a random direction and stagger around for 100,000 years looking for the exit. A neutrino barely notices the plasma is there. It passes through the entire sun, through 700,000 kilometers of the densest material in the solar system, in about 2 seconds. 2 seconds. To a neutrino, the sun is as transparent as open air is to a photon, and then it crosses space at very nearly the speed of light, and it arrives at Earth in about 8 minutes, roughly the same time as the light from the photosphere, and it passes through the Earth as well as if it were not there. At night, right now, while you are lying in that room in the dark, solar neutrinos are passing up through the Earth and through the floor and through your mattress and through you, at a rate of about 65 billion of them per square centimeter of your body per second. 65 billion per square centimeter per second passing through you as if you are not there. During the day, they come down from above. During the night, they come up from below because they have passed through the entire solid mass of the Earth on their way to you. And the Earth, that solid, rocky, heavy planet beneath your bed, is no more of an obstacle to them than a pane of glass is to sunlight. So physicists built detectors, enormous, deeply buried, extraordinarily sensitive detectors, tanks filled with tens of thousands of tons of water or dry cleaning fluid placed deep underground to shield them from cosmic rays and background radiation, all in order to catch the extraordinarily rare occasions when a solar neutrino happens to interact with something in the detector. Most pass through, almost all pass through, but just a few out of the trillions of trillions arriving leave a tiny detectable signal, and from counting those signals, scientists could measure how many neutrinos the sun was producing per second, and from that number they could calculate what was happening in the core. This is how we know the fusion model is right, not because we went there, because the sun told us, in the only language that could escape from its interior without modification, the language of neutrinos. But there was a problem. For decades, the number of neutrinos being detected did not match the prediction. The sun was producing fewer than expected, significantly fewer, roughly a third of what the models said there should be. And this was troubling. It meant either our understanding of the sun's core was wrong, or our detection method was failing, or something else, something unknown, was happening to the neutrinos on their way from the sun to the detector. This was called the solar neutrino problem, and it was one of the most important unsolved questions in astrophysics for the better part of the latter half of the 20th century. beginning in the 1960s when Raymond Davis Jr. began taking the first careful measurements in a detector deep in a gold mine in South Dakota. The problem persisted for decades. The number was always too low. And then at the turn of the millennium, the answer arrived. Neutrinos, it turns out, come in three varieties, three flavors, physicists call them, with characteristic delight in informal language. There is the electron neutrino, which is what the sun's fusion reactions produce, but there is also the muon neutrino and the tau neutrino. And neutrinos can transform, oscillate, between these flavors as they travel. The sun produces electron neutrinos, but by the time they reach a detector on Earth, some of them have become muon neutrinos or tau neutrinos, and the early detectors were only sensitive to electron neutrinos, so they were catching only the ones that had not yet oscillated into a different flavor, roughly a third of the total, which is exactly what was being measured. When detectors were built that could catch all three flavors, most notably at the Sudbury Neutrino Observatory in Canada, which began taking data in the late 1990s and reported its key results in 2001 and 2002, the total number of neutrinos arriving from the Sun matched the predictions of the fusion model almost exactly. The solar neutrino problem was solved, but the solution was more than just a confirmation of the Sun's interior. It was also the first clear evidence that neutrinos have mass, a finding with deep implications for particle physics, implications that reach far beyond the Sun. The Sun, in proving its own fusion model correct, simultaneously helped prove a new and important piece of fundamental physics. The Sun proved the theory, and the theory proved the Sun. This is, to me, one of the quieter and more beautiful moments in the history of science, a problem that seemed to cast doubt on our understanding of the most important star in the sky, and whose resolution not only confirmed that understanding, but enriched our picture of the universe in ways nobody had quite anticipated. A discrepancy that turned out to be a discovery. And it means that everything we have been tracing tonight, the 15 million Kelvin core, the proton-proton chain, the billion-year wait, the quantum tunneling, the 100,000-year random walk through the radiative zone, the boiling convective zone, and its Texas-sized granules, the photosphere at 5,800 Kelvin, where the light finally steps free. All of it is confirmed, not guessed, not theorized, and left uncertain. Confirmed by the neutrinos that slipped out through the back door of the Sun while the light was still finding its way through the crowd. We know what happens in the heart of a star. And we know it beautifully without having to go there. So let us take a breath. Let us settle where we are. If you are still awake, or if you drifted for a moment and have come back, which is perfectly fine, the Sun's physics will wait for you. Then perhaps you can hold in mind the shape of what we have traced so far tonight. The core, where it is impossibly dense and impossibly hot, where protons wait 1 billion years for a chance to tunnel through the wall they cannot climb. The energy that results, born as a gamma ray, beginning its century-long stumble outward through the radiative zone, the convective zone where the plasma boils in great rising and falling columns, topped by a mosaic of Texas-sized granules, simmering and dissolving. And then the photosphere, the surface where light steps into space, and the 8-minute sprint to your eye begins. And threaded through all of it, the neutrinos, almost massless, almost invisible, oscillating between flavors as they travel, carrying in their numbers the proof of everything we have just described. That is how the energy gets out. And now we are ready, nearly ready, for the final piece. The piece that completes the promise we made at the beginning. The piece that turns everything we have learned tonight into something you can take outside on a clear night and use. Something you can see with your own eyes. Because we have not yet talked about what happens to the light once it is out. We have not yet asked why some stars are blue and some are red. We have not yet revealed the reversal. The thing that once you know it, you can never unsee when you look up at the sky. But we are almost there. The energy is free. It is crossing space toward your eye. And the color it carries when it arrives, that is the last and most satisfying part of the story. We have earned it. And we will take it slowly because that is the only way worth taking any of this. But before we do, while you are resting in that space between one thought and the next, in that comfortable place where the mind is soft and the body is still, just let the image settle for a moment. The light on your skin tomorrow morning. The energy in it, born in the sun's core perhaps 100,000 years ago, as a gamma ray that would have killed you if you had been there to receive it. That energy, stumbling through the densest, most extreme region in the solar system for longer than the entire span of recorded history, transformed along the way from violent to gentle, from gamma to something softer, rising through the boiling convective zone, emerging at the photosphere, crossing 150 million kilometers of empty space in 8 minutes, and arriving at your window as a soft rectangle of morning light. You will sleep in that light tonight, in a sense, even if your curtains are drawn. The neutrinos from the same fusion reactions are passing through you right now, 65 billion per square centimeter per second, gentle and unnoticed. The sun is present in this room, in this moment, in the most literal way imaginable. Rest here for a moment, and in the next part of our journey we will follow the light all the way to its color, and we will finally read the thermometer that the sky has been holding up all along. So, the color. We have followed the light from its first impossible breath. Born in a place denser than any metal you have ever held, under a pressure that would crush the concept of solid matter at a temperature so extreme that ordinary physics quietly steps aside and lets the strange rules take over. We have watched it tunnel through a barrier it had no right to cross. We have watched the energy stagger through the radiative zone for longer than the whole of human civilization, stumbling in no particular direction, absorbed and reborn, and absorbed again, 100,000 years of wandering through 1,000,000 kilometers of plasma. We have watched it rise through the boiling outer third of the sun, lifted on columns of hot gas the size of Texas, rising and cooling and sinking and rising again, and we have watched it finally cross the photosphere, that last transparent threshold, and launch itself across 150 million kilometers of empty space in just over 8 minutes. And now it arrives at your eye, or at the eye of anyone looking up on any clear night anywhere on Earth. And when it arrives, it carries something with it, something you can see, something you can read, if you know the code. It carries its color, and the color tells you everything. Let's take that slowly because it really is the most satisfying part. And it is also the part most people never quite receive in full. You already know, in the way that you have known things since childhood, that hot things glow. You have seen it. A piece of metal heated in a flame goes from dull grey to a faint red glow to a brighter orange to a yellow-white. The element on an electric stove, when you turn it to maximum, glows red. The filament in an old incandescent light bulb glows orange-white. A welding arc, much hotter, burns bluish-white. You have seen this progression, perhaps without stopping to ask what it means. The hotter the object, the bluer the light it produces, the cooler it is, the redder. This is not an accident of the particular material. It is not because iron behaves one way and tungsten another. It is a universal law that applies to every object in the universe, every object that has a temperature. which is to say, every object that exists. The law has a name. It is called black body radiation. And despite the name, which makes it sound like something technical and remote, it is describing the most ordinary thing: the relationship between how hot something is and what color of light it produces. The reason it is called black body is a little ironic and worth a moment of your sleepy attention. A perfect black body, in the physicist's language, is an object that absorbs every single wavelength of light that falls on it. It reflects nothing. And precisely because it absorbs everything, when it is heated, it radiates purely, without contamination from any particular material's chemistry. It is a perfect emitter. Real objects like stars are not perfect black bodies, but they are close enough that the relationship holds beautifully. And the relationship is this: heat something hotter, and the peak color of the light it emits shifts toward the blue end of the spectrum. Cool it down and the peak shifts toward the red. This was formalized by a German physicist named Wilhelm Wien in 1893, and the relationship carries his name, Wien's displacement law. The peak wavelength of the light an object emits is inversely proportional to its temperature. If you double the temperature, the peak wavelength halves, shifting toward the violet. If you halve the temperature, the peak wavelength doubles, shifting toward the red. The mathematics behind this is not something you need to carry into sleep with you. What you need is the image. And the image is this: a thermometer made of color. Every hot object is broadcasting its temperature in the only language it has, which is light. And if you know the code, you can read the temperature from the color alone, from across a room, from across a continent, from across light years of empty space. Stars are hot objects, stars glow, and so without any instruments more sophisticated than your own eyes, you can look at a star and know something true about it, something real and physical, not poetic or mythological, but a literal measurement. You can read its temperature. Now here is the part that I want you to sit with for a moment, because it is genuinely surprising, and it is the piece that, once you have it, changes the way you look at the night sky forever. We code red as hot and blue as cold. It is one of the most deeply embedded visual associations in human culture. The tap with the red mark is the hot one. The warning light on the dashboard is red. The flame in a children's drawing is orange and red. Red hot is a phrase that means the maximum of heat and danger and intensity. Blue, by contrast, is the color of ice, of winter, of cool water, of calm. The sky does not agree. In the sky, in the language of physics, the code is exactly reversed. Blue means hot, red means cool. Blue stars are the hottest stars in the sky. Their surface temperatures can reach 10,000 Kelvin, 20,000, 40,000 and beyond. Temperatures that make the Sun's 5,800 Kelvin surface seem almost modest. Red stars are the coolest. Their surfaces hover somewhere between about 2,500 and 3,500 Kelvin, still of course extraordinarily hot by any everyday measure, but cool in stellar terms, cool enough that the peak of their radiation has shifted all the way into the red and orange end of the spectrum, which is why they appear the color they do. And the Sun, our yellow-white, mild, familiar, patient Sun, sits in the comfortable middle of this range. Its surface at roughly 5,800 Kelvin is warm enough to peak somewhere near the green part of the spectrum, but it emits broadly enough across all visible wavelengths that it comes across to the eye as white or pale yellow. It is a temperate, middle-of-the-road sort of star, and its color reflects exactly that. The night sky, in other words, is a thermometer, a vast, ancient, silent thermometer calibrated in Kelvin, displaying readings in color. And the reading is the reverse of the one on your bathroom taps. Blue is the furnace. Red is the ember. Once you know this, You cannot unsee it. And the wonderful thing, the thing I find quietly beautiful about this, and I hope you will too, is that you do not need a telescope to see it. On a clear night, with nothing more than your own unaided eyes, you can look up and take the temperature of stars that are hundreds or thousands of light years away. The information is right there, encoded in the color, waiting for you to read it. Or let me give you an anchor, a real, specific, named anchor that you can take outside with you. Orion. Orion is one of the most recognizable constellations in the sky. In winter, in the northern hemisphere, it rises in the eastern sky in the evening and stands high above the horizon by midnight, the great hunter with his belt of 3 stars and his club raised and his bright shoulders and knees. It is one of the few constellations that really does look a little like what it is supposed to be, which is rare and pleasing. Now look at the 2 brightest stars of Orion, not the belt, the corners. The upper left corner of Orion, the star that marks one of his shoulders, is Betelgeuse. Say it however feels natural to you. Betelgeuse is the common English pronunciation, though the original Arabic name is older and stranger and lovelier than any pronunciation fully captures. Betelgeuse is red, unmistakably, visibly, beautifully red-orange, even to the naked eye if you spend a moment with it. And according to everything you now know, that color tells you its temperature. Betelgeuse's surface is around 3,500 Kelvin. Cool, in stellar terms, an ember. Now look at the lower right corner. The star that marks one of Orion's feet, or knees, depending on which version of the myth you prefer. That star is Rigel. Rigel is blue-white, bright, sharp, cool-toned to the eye, and its color tells you that its surface is around 12,000 Kelvin, more than twice as hot as our Sun, more than 3 times as hot as Betelgeuse. Betelgeuse and Rigel, both visible on the same winter night, both bright enough to see with the naked eye from almost any location on Earth that isn't swamped with light pollution. One red, one blue, one cool, one hot, sitting in the same constellation, appearing to the casual eye as simply 2 of the bright stars in Orion, but actually broadcasting their temperatures in color as they have been doing for millions of years, waiting for someone to know the code. Now you know it. You can look up at Orion on the next clear night and take the temperature of 2 stars simultaneously with no instrument more advanced than the eyes you were born with. That is, I think, a rather wonderful thing to be able to do. And while we are in Orion's neighborhood, let's turn a little way south and east in the sky to a neighboring constellation called Scorpius. There you will find another brilliant red star called Antares. Its name, in ancient Greek, means something close to rival of Mars. And indeed, to the ancient observers, the reddish glow of Antares was easily confused with the reddish glow of the planet Mars, which wanders through that part of the sky periodically. Both red, both prominent, both low in the southern sky. Antares is red for the same reason Betelgeuse is red. It is cool at the surface, cool in stellar terms with a surface temperature in a similar range to Betelgeuse. It too is an enormous star, a red giant puffed up to extraordinary size while cooling at the surface. But we will come to the question of size and age in a moment. First, the ladder. Astronomers, over the past century or so, developed a classification system for stars that turned out to be, at its heart, a temperature ladder. The system, in its modern form, sorts stars into 7 categories based on the characteristics of their spectra, the particular wavelengths of light they absorb and emit, which carry information about both temperature and composition. The categories, from hottest to coolest, are labeled O, B, A, F, G, K, and M. O stars are the hottest, blue-white, searing with surface temperatures above 30,000 Kelvin. They are rare, brilliant, and, as we shall come to, short-lived. B stars are slightly cooler but still very hot, blue-white in the range of 10 to 30,000 Kelvin. Rigel is a B-type star. Stars are white, around 7,500 to 10,000 Kelvin. Sirius, the brightest star in the night sky, the Great Dog Star, is an A-type star. F and G stars are yellow-white, in the range of roughly 5,000 to 7,500 Kelvin. Our Sun is a G-type star, specifically a G2V, a classification that places it squarely in the warm, stable, medium mass, middle temperature category of stars, the kind of star most hospitable to long, slow, patient burning, the kind of star that can hold its hydrostatic equilibrium for 10 billion years and barely seem to notice. K stars are orange, cooler, in the range of 3,500 to 5,000 Kelvin, and M stars are the coolest, red, with surface temperatures below about 3,500 Kelvin. Betelgeuse is technically an M-type star, as is Antares. Red dwarfs, the smallest, most common stars in the galaxy, are also M-type, though they are dim and cold, where Betelgeuse and Antares are enormous and relatively bright. The sequence runs O, B, A, F, G, K, M, from the blue-hot furnaces at the top to the red, cool embers at the bottom. Generations of astronomy students have remembered it with a mnemonic, "Oh, be a fine girl, kiss me," or "Oh, be a fine guy, kiss me," depending on who is teaching. There are others, more elaborate and sometimes more colourful, that I will leave to your imagination. The mnemonic is silly, as all the best mnemonics are, and it sticks, and that is the point. But underneath the silliness is the temperature. Always the temperature. Obaf Kiem is a thermometer written in letters. And now a small, delightful aside that I think you will enjoy. You have probably at some point bought a light bulb, or your home uses a kind of light bulb, and that is described on the packaging as warm white or cool white. Warm white bulbs produce a soft, amberish, golden sort of light. Cool white bulbs produce a crisper, bluer, more neutral light. And here is the thing, the terminology in the light bulb aisle is accidentally using the physics of blackbody radiation, but with the emotional labels stuck on backwards, exactly the way our tap convention does. A warm white bulb is actually producing light at a lower color temperature, typically around 2,700 Kelvin. A cool white bulb operates at a higher color temperature, 5,000 Kelvin or above, and its light is actually hotter in the physical sense, closer to what you would expect from a hotter, bluer star. We call the cooler light warm because it is amber and cozy and reminds us of firelight. We call the hotter light cool because it is crisp and blue and reminds us of daylight on a winter morning. And so the labels in the hardware store invert the physics for the entirely human and understandable reason that our feelings about color run in the opposite direction from the physics of how color is produced. The universe says blue is hot, red is cool. Our intuition says red is hot, blue is cool. Even in the fluorescent lit aisle of a hardware store, the physics is quietly insisting on its version, and the labels are cheerfully ignoring it. There is something reassuring in that, I think. The universe has its own logic, running patient and deep underneath our human conventions. And the conventions are not wrong exactly. Fire is warm, ice is cold, and those associations make sense within the narrow band of human experience. It is just that the universe, operating across ranges of temperature that would vaporize any fire or any ice in an instant, has its own color code, and it runs in the other direction. Now I want to say something about the sun's own color, because it is one of the facts in this story that I find unexpectedly pleasing, and I think you will too. The sun, from Earth, looks yellow. On a clear day, it is unmistakably golden or yellow or orange, depending on how high it is in the sky. In paintings and in children's drawings and in every cultural tradition I can think of, the sun is yellow. And yet, the sun, seen from space, seen without the intervention of Earth's atmosphere, is white. Not pale yellow, white. It emits light fairly evenly across all the visible wavelengths. It has a slight peak toward the green, but it spreads broadly enough across red, orange, yellow, green, blue, and violet that those wavelengths blend to produce white light, the way all the colors blended together do. The yellowing happens here, at the bottom of the atmosphere, as the sunlight passes through kilometers of air on its way to your eye. The atmosphere preferentially scatters light at the blue end of the spectrum, a phenomenon called Rayleigh scattering, after the physicist Lord Rayleigh, who worked out the mathematics of it in the 19th century. Blue light has a shorter wavelength than red light, and shorter wavelength light is scattered more efficiently by the small molecules that make up our air. So the blue light bounces around the whole sky. It is the blue light scattered sideways and downward that makes the sky appear blue. And the direct sunlight, having lost much of its blue component in that scattering, arrives at your eye, yellowed or orange or red at sunset, when it is traveling through an even thicker slice of atmosphere and losing even more of its blue. The sun is not yellow, the sky is yellow, filtering the sun. The actual color of the sun, the color it would show you from the airless surface of the moon, is white. And so the sun is white by temperature and yellow by atmosphere. A star in the middle of the spectral sequence, a G2V on the temperature ladder, broadly emitting across all visible wavelengths, intercepted by a thin shell of gas that scatters the blue sideways and softens everything that gets through. It is, in its way, a completely ordinary and completely wonderful thing. Let me rest here for a moment on the question of what a star's color tells you beyond its temperature, because there is a little more, and it is worth having. The color of a star gives you, very approximately, a sense of its age and its fate. Not with precision. Not the way a birth certificate gives you an age, but in broad strokes, in the general shape of a story. Blue stars are the O and B types. The blazing furnaces at the top of the temperature ladder are enormous. They are many times the mass of our sun, sometimes dozens of times. And all that extra mass means all that extra gravity pressing inward, which means the core must generate energy at a furious rate to maintain hydrostatic equilibrium, to keep itself from collapsing. And generating energy at a furious rate means burning through the hydrogen fuel at a furious rate. The great blue stars are prodigal. They spend their fuel as fast as they can, living brilliantly and briefly. A massive O-type star might shine for only a few million years before exhausting its hydrogen and collapsing and exploding in a supernova. A few million years sounds like a long time by human standards, but on the cosmic calendar, it is almost nothing. The Earth is 4,600 times older than that, and the Sun has been burning for 4,600 million years already. The blue stars you see in the sky are the newest, the youngest dying. They are not long for the universe. They burn hard and fast, and when they go violently. Supernovae, the most energetic events short of the Big Bang itself, seeding the surrounding space with all the heavy elements their cores have forged. Red dwarfs are the opposite in almost every way. Small, perhaps a tenth of the mass of the Sun, sometimes less. Cool at the surface, dim, quiet. They burn their hydrogen so slowly at such a measured pace that a red dwarf star can shine for tens of billions of years. Some models suggest the smallest red dwarfs could remain on the main sequence, stably fusing hydrogen in their cores, for trillions of years. Not billions, trillions. The current age of the universe is approximately 13,800,000,000 years. A red dwarf born at the beginning of the universe, at the first moment stars began to form, would still be in its stellar youth by now. The smallest red dwarfs alive today will still be burning when the universe is 100 times older than it currently is. They will still be burning when all the blue stars are long gone, when all the sun-like stars have swelled into red giants and shed their outer layers and cooled into white dwarfs. When the night sky has changed beyond recognition from anything we can see tonight, the red dwarfs will still be there, dim and patient, and very quietly getting on with it. Blue is young and fast and brief. Red is ancient and slow and will outlast nearly everything. The night sky, in that sense, is not just a thermometer. It is also a kind of clock and a kind of biography. Each star's color, a small note about who it is, how quickly it burns, how long it has been here, how long it has left. And here is something that I want you to carry with you, something that connects the stars to you in a very specific and physical way. Our sun is, in cosmological terms, a third-generation star. The universe, in its first moments, produced primarily hydrogen and helium. The first stars were made of almost nothing else when those first massive stars, blue giants, almost certainly hot and profligate, burned through their hydrogen and died in supernovae. They scattered the heavier elements they had forged into space. Carbon, nitrogen, oxygen, iron, calcium, and all the rest, forged in stellar cores and in the violence of the explosion itself, flung out into the interstellar medium. A later generation of stars formed from that enriched material, lived and died in their turn, and scattered still more heavy elements. And then, about 4,600 million years ago, in a quiet corner of the Milky Way galaxy, a cloud of gas and dust, enriched by at least 2 previous generations of stellar death, collapsed under its own gravity and formed our sun, and the disk of leftover material that condensed into our planets, and eventually into everything living on one of those planets. The carbon in your body, in every cell, in every strand of DNA, in the structure of every protein, was forged inside a star that died before the sun existed. The oxygen you breathe was made in stellar cores, the calcium in your bones, the iron in your blood, all of it stellar material, all of it the residue of suns that burned and exploded and gave their substance back to the cosmos. You are not merely watching starlight, you are made of it. Or more precisely, you are made of what stars made and died to release. The atoms in your body have been inside at least one star, possibly more, before they found their way into a cloud of dust, then a planet, then a living thing, then you. When you look up at the stars, you are not entirely separate from them. You are, in a very real sense, stardust looking at the furnaces that made it. I find that an extraordinarily settling thought, not grandiose, just true and quiet and strangely comforting. The universe made you out of itself through fire and time and patient gravity, and now a small piece of it is lying in a bed, looking up at a ceiling or out at a window, and the light from those ancient furnaces is falling gently through the dark. There is one more thing I want to tell you about the light in the sky, and it is a thing about time. You know now that the energy in a beam of sunlight spent tens of thousands of years, perhaps 100,000 years or more, making its slow, stumbling, random walk from the sun's core to its surface. And you know that it then crossed 150 million kilometers of space in 8 minutes and 20 seconds. But consider the starlight, the light from a star that is not our sun. The nearest star system to our own, Alpha Centauri, is about 4.2 light-years away. The light you see from it tonight left it 4 years ago. You are not seeing Alpha Centauri as it is tonight. You are seeing it as it was 4 years ago, before whatever has happened there since, if anything has happened at all, which being a quiet and stable system, it almost certainly hasn't. Sirius, the brightest star in the night sky, is about 8.5 light-years away. The light you see from Sirius tonight left it 8.5 years ago. Rigel, the blue-white beauty in Orion's foot, the star whose temperature you can now read in its color, is about 860 light-years away. The light from Rigel that reaches your eyes tonight left that star sometime around the year 1160 or so, when much of what we call medieval history was still unfolding on Earth. Betelgeuse is somewhere between 400 and 550 light-years away. Its distance is genuinely uncertain, one of the honest, open questions of modern astronomy. The light you see from it tonight left it between 400 and 500 years ago, somewhere in the period of the Renaissance, the early printing press, the first circumnavigation of the globe. And now add to that the random walk. The light that left Betelgeuse 4 centuries ago heading toward your eye. That light was produced in Betelgeuse's core 100,000 or more years before it ever reached the surface, before it could even begin its journey through space, before you could even start counting the light travel time. The double delay in Starlight, the slow walk out of the star, the long crossing of space, and then the brief, instantaneous final moment of arrival at the retina. The whole journey from fusion event to perception is a chain of timescales that span from milliseconds to hundreds of thousands of years, all compressed into a single instant of seeing. When you look at a star, you are seeing something that is genuinely multiply ancient, not just in the poetic sense, in the literal, precise, physically measurable sense. The light has been traveling through the interior of a star and then through empty space for longer than you can easily hold in your mind. And it arrives, after all of that, as a soft point of light, patient, quiet, asking nothing. I want to stay with that for a moment because I think it is worth inhabiting before we close. You are lying right now, wherever you are, whatever time it is in your corner of the world, in a room that is threaded through with starlight. Some of it visible if a window is near, some of it blocked by walls and curtains and the thickness of a city's glow, but present nonetheless outside, in the air, on the skin of the building around you. The neutrinos we talked about earlier in this journey, 65 billion of them passing through every square centimeter of your body every second, they are passing through you right now, the direct messengers from today's fusion reactions in the sun's core, carrying their tiny energies straight through the earth and through you and out the other side without noticing you at all. And the light, the visible light from the sun, the light that will come through your window in the morning, that light has already made its journey. Some of it is waiting in the sky right now, on the far side of the earth, making morning for someone else, and it will reach you in a few hours. That light spent its 100,000-year random walk through the sun, crossed 150 million kilometers of space, was scattered and softened by the atmosphere, and will arrive at your window as something warm and ordinary and kind. There is no better word for it, I think. Kind. Not because light has intentions, but because that is the texture of the experience, a thing that was born in unimaginable violence, under conditions that would destroy anything we know, passed through extremes of density and temperature and chaos, and arrived at your window as something you can let fall on your face and feel as warmth, and ask no more of it than that. The whole universe, in that sense, is making this small gift to you every morning. We set out at the beginning of this journey with a question that sounded simple and turned out to be bottomless. How is starlight made? And we followed it all the way down. We went into the core to 15 million Kelvin, to a density 13 times that of lead that somehow remains a gas, to a pressure of 250 billion atmospheres, balanced so perfectly by the outward push of radiation that the sun has held that balance for 4.5 billion years without flinching. We watched two protons attempt something that they have almost no chance of doing, one of them waiting, on average, 1 billion years before the moment arrives, and then, at the moment of near contact, not quite strong enough, not quite fast enough, not quite hot enough to do it by brute force, and tunneling through the barrier anyway because the universe has a loophole, and the loophole is called quantum mechanics. We watched the chain of reactions, deuterium to helium-3 to helium-4, 2 positrons and 2 neutrinos released, and a tiny fraction of mass, 0.7%, converted into energy by the most famous equation anyone has ever written. 4 million tons of mass per second becoming light, 600 million tons of hydrogen fused every second, and still the sun barely notices because it is so vast and because the process is so patient that it can sustain this rate for 10 billion years and still have fuel to spare. We learned that the core's power density, the energy produced per cubic meter, is barely more than a compost heap, that the sun shines not because it is intense, but because it is enormous, an important distinction and a quietly calming one. We watched the energy begin its journey outward, not as a straight flight, but as a stagger, the random walk through the radiative zone, absorbed and re-emitted, scattered in every direction at once, traveling what amounts to a galaxy's worth of distance inside a star that is a mere 1.5 million kilometers wide. We learned that this journey takes somewhere between tens of thousands and a few 100,000 years, longer than our entire recorded history, longer than the span of human civilization from its first clay tablets and cave paintings to this very night. We watched the energy rise into the convective zone, lifted on columns of boiling plasma, carried to the surface in churning cells the size of Texas that form and dissolve every 8 to 20 minutes, a constantly renewing surface of light. We arrived at the photosphere, 5,778 Kelvin, the layer where the plasma finally becomes transparent enough for light to escape freely, and we watched the photon launch itself across the solar system and arrive at your eye in 8 minutes and 20 seconds-ish. We learned that the neutrinos, born in the same reactions, take a different path, escaping the core in 2 seconds, crossing space in 8 minutes, passing through the whole Earth and through you without stopping, 65 billion per square centimeter per second, gentle and undetected. And then we came to the color. Black body radiation, Wien's displacement law. The peak of the glow shifts toward blue as the temperature rises, toward red as it falls. The night sky, a thermometer in reverse of everything our intuitions tell us. Blue for hot, red for cool. O, B, A, F, G, K, M. A ladder from the blue furnaces to the red embers, and our sun, a G2V, comfortably in the middle. Orion on a winter night, Rigel 12,000 Kelvin, blue-white, blazing, Betelgeuse 3,500 Kelvin, red, cool, vast. Vast enough to swallow the orbit of Mars if it were placed where our sun is. 2 stars in one constellation, one hot, one cool, their temperatures visible without instruments, and the deeper truth beneath the color that blue stars are brief and red dwarfs are eternal, that the brightest, hottest stars in the sky are burning through their fuel so fast that they will be gone in a few million years, while the dim red sparks you can barely see will still be burning long after every other kind of star has faded. And the deepest truth of all, that the atoms in your body were forged in stars that died before the sun existed, that you are made of old starlight, literally, carbon and oxygen and iron and calcium distributed through space by stellar deaths, gathered by gravity, incorporated into a planet and into a living thing and into you. The light you see and the substance you are made of have the same origin. You are looking at the furnaces that built you. That is what the question, how is starlight made, opens into if you follow it all the way down. Not just physics, not just equations, but a sense of belonging to a process that is older than this planet, vaster than this solar system, patient beyond any timescale. Human beings were evolved to intuitively grasp. And here you are, a small, warm, temporary arrangement of atoms forged in dead stars, lying in a bed on a planet circling one of those stars, while the light from 100,000 others falls quietly on the sky outside your window. That is, I think, an entirely sufficient thing to be. I want to ask you something before we close. Where are you listening from tonight? What time is it in your corner of the world? Is there a lamp still on somewhere nearby, or has the room gone dark? Is it winter, and is the sky clear enough to find Orion if you looked? I ask because this conversation, this slow walk through the physics of light, has been happening wherever you are. The same facts, the same patient journey, the same ending, whether you are in a city where the stars are mostly hidden, or in a place dark enough to see the Milky Way as a soft smear across the sky. Whether it is early in the night or nearly morning. Whether you are already drifting or still sharp and listening to every word. The light is out there either way. The neutrinos are passing through you either way. The sun is fusing hydrogen in its core either way at the same rate it has been fusing hydrogen for 4.5 billion years, and will continue to do so for approximately another 5 billion years, long enough that the word long enough barely captures it. If you enjoyed this slow walk, if this was a good way to spend the hours between waking and sleep, a quiet like or subscribe would mean more than I can easily say. Small channels like this one run on that kind of support. It is how these nights keep coming, how there are more quiet journeys waiting for you. And if you want to leave a note in the comments telling me where you are listening from and what time it is in your part of the night, I would genuinely love to know. There is something lovely about the idea of all those different corners of the world, all those different time zones and weather patterns and kinds of darkness, all connected by the same story about light. Thank you for staying. Thank you to those of you who have been here for other journeys. Your presence is what makes this worth doing. Now, the physics is complete. The story is told. The light has made its journey, and so have you. The fusion is happening right now in the sun's core, as it has been happening every second of every day of your entire life and everyone's life before you, and as it will continue to happen long after the names of everyone alive tonight have been forgotten. The photons are stumbling through the radiative zone on their 100,000-year walk. The convective cells are rising and falling on the sun's surface, each one the size of Texas, each one lasting only minutes before dissolving and reforming. The neutrinos are passing through you. The light from Rigel that left that blue star 8 or 9 centuries ago is crossing the last few kilometers of its journey through Earth's atmosphere right now, heading for some eye that may or may not be open to receive it. And somewhere in all of that, in the vast, unhurried machinery of nuclear physics and thermal radiation and empty space, the piece of it that reaches you is, by the time it arrives, gentle. That is the thing I most wanted to leave you with, not the numbers, though the numbers are real and true and in their way beautiful. Not the equations, though Wien's law, and the proton-proton chain, and the random walk are genuine and precise descriptions of how the universe actually works. But the texture of it, the quality of the light after its long journey, the way something born in the most violent place in the solar system arrives at your skin as something you can barely feel, the patience of it, the scale of it, and the smallness and warmth of the moment of arrival. You are made of stars. The light falling on you is ancient. The sky above you is a thermometer, written in blue and red, and every shade between. And none of it is asking anything of you tonight except to rest. Calm mind, clever dreams. I'll be here tomorrow night.